Hi folks, welcome back. I hope you're all doing well. The paper I'm looking at today is from the very recently concluded PLDI 2020, and this caught my interest because it's a mix of machine learning and programming languages. The system that the authors propose over here applies a machine-learned model to predict types in a dynamically untyped language like Python. And they get some pretty decent results as they show over here, so let's dive into the paper and see how they do this. So in the last few years, we've seen that programmers in the dynamic typing camp have come around to recognizing the benefits of static typing. And we've seen the rise of a lot of optional typing systems. For example, in Python 3, you can now annotate your variables, both parameters as well as return types from functions and so on, and then you can optionally type check them. The problem really is that when you start with a code base without any annotations, it's a lot of work to add type annotations to it. And this really is the core problem that this tool is trying to solve. It wants to expand your coverage of type annotations by suggesting types out of a dynamically typed code base which doesn't have these annotations or has very few of these annotations. One important thing to keep in mind is that what the authors found was that the distribution of types follows a very power law kind of distribution, in that a very small number of types account for the vast majority of type annotations. These are the common types like string or int or bool. But then the vast majority of types are used at very few locations, but they do account for the majority of types. This means that some prior approaches to this kind of type suggestion, which relied on classification, are not really going to work because they cannot predict types that they have not already seen. This is one key advantage of Typilus, in that it can predict types that it has not seen during training. Now, the paper has a fair amount of math related to machine learning and loss functions and so on in it, and I won't go into much detail into all the math behind this. My goal is to give you a high-level overview that hopefully gets you curious and makes you look at the full paper yourself. But at a very high level, this is how Typilus works. It takes in code with type annotations and passes them through a graph neural network. And we'll talk in just a bit about why it uses a graph neural network. And the output of this training is an embedding in d-dimensional space. This is what the authors call a type space. This type space is then used for inference or for predicting types. So now on the inference side, you have some partially annotated code and you want to make type predictions for the unannotated variables in it, for example. And what you do is you project that into this type space and you look at the k nearest neighbors, so the types around where your projection lands. And those are the ones you consider as candidate type suggestions. These suggestions are then passed through a type checker to see which ones are valid. And that leaves you with a valid set of type predictions along with some confidence numbers on how good the model thinks they might be. The reason they use a graph neural network is because they want to capture all the structure in the source code. This includes low-level things like token and syntax, but also higher-level things like the tree structure of the abstract syntax tree of the programs that it is training on. Here is an example of a graph for a very simple code snippet, and you can see how it captures not just the abstract syntax tree, but also tokens and identifiers and the relationships between the use of identifiers and so on. And it is all this rich, graphically interconnected information that is fed into the graph neural network for training. And the end result of this training is projecting the set of types that it found in its training set of programs into a multi-dimensional real space. The important thing is that this space is open in the sense that it does not partition the space into a finite set. It can represent an open vocabulary of types. So every symbol has an embedding in this multidimensional real space. To predict the type, you take a symbol and project it into the space and then look at the nearest neighbor types in that space. The other interesting thing is the loss function they use when training, and they use something called a triplet loss function. And this basically has the effect of pushing away points that are dissimilar to the point you're looking at and pulling in points that are similar. Now let's look at some of the results they got. The authors have implemented this scheme for Python, and that is a good choice because, of course, Python is originally designed to be a dynamically typed language without any type annotations. But over the last couple of years, it has got some language features that let you put some optional type annotations, and these can be checked by a type checker. To evaluate the performance, the authors get some Python projects out of GitHub that do already have some type annotations, and then measure it along two axes. The first one is how often the types predicted by Typilus match the annotations that are already in the code. And then they try to predict types for symbols that do not have types already annotated on them and see how often those pass the type checker. For the first test, they take some existing code, delete all the type annotations, and then try to predict those types again and see how well the original and the predicted types match. And when you do this, you could have one of three results. The types could match exactly. The types could match up to a parameter. So list of something. If you predicted list, that's good enough. Or the types could be interchangeable when optionally typed. And these are the results they get. You can see that they've broken it down by common types and rare types. As you can see, they perform much better on common types than on rare types. But overall, they find that for 70% of the symbols, they can achieve a type neutrality of about 95%, which means that this method is actually good enough for integration into a tool. The flow would still have the programmer in the loop in that this tool would make type suggestions and the programmer would look at them and choose which ones to accept. So it doesn't have to be perfect, it just needs to make reasonable suggestions to improve the overall productivity of the programmer. In the next test, they tried to see how well Typilus can predict the types on new symbols that don't have type annotations, and whether those types pass the type checker. And they got pretty decent results here. They found that 89% of the predictions did pass the type checker. That was 89% for MyPy and 83% for the PyType type checker. Interestingly enough, when they were doing this, they found some existing type annotations that were incorrect in some fairly well-known GitHub repositories. So that was a quick look at a paper that tries to predict types in dynamically optionally typed languages using a graph neural network, and then implement it for Python and get some very promising results for suggesting types in Python. I hope you enjoyed that, and I will see you next time. Thank you very much.